Okay, so for this lecture, we're going to look at heuristic solutions to optimization problems. Now, most of the things we've seen up to this point have been dealing with linear programs, where we have very strict definitions on what we're trying to optimize. We have straight lines, we have linear objective functions. This is going to be a little bit of an introduction to what happens when you aren't in that nice, neat little box. When we have linear programs, we have some techniques that we've seen, the simplex method and the derivatives of it, that will solve these problems very efficiently. But that's a very small subset of things that you will see in optimization. And normally you don't have that nice little box to work in. So we're going to take a look at heuristic solutions to optimization problems. So what I mean here by heuristic solution? I mean that this is an algorithm where you can come up with a solution that is a good solution, but isn't really guaranteed to be the exact best solution. The simplex method gives you the optimal solution. Heuristics will give you a very good solution. Sometimes it'll be the optimal solution, sometimes it won't, but it's techniques that will get you close. Why would you do that? Well, sometimes it's impossible to get the exact answer for whatever reason. There's too much, for whatever reason, you just can't get the exact answer if there's too much detail, uh, too many variables, so forth. Sometimes it would be possible to get the exact answer, but the computational cost of it is extreme. So when you have a good answer, when you're close enough, you say that, the added cost, the added resources that I would need to get the exact solution just aren't worth it. I'm happy with what I have. So you work with a good enough solution. You can also be in a situation where you could conceivably get a better answer, but as we've seen, when you're dealing with real world solutions, especially, there's fuzziness, there's unknowns. So sometimes those unknowns and uncertainty just outweigh the incremental improvement. Your unknowns are just more than the added value you are going to get by pushing your solution even farther. So sometimes all you need is a good enough solution. So a little diversion into kind of the difficulty of finding solutions. There's more to it than what we're going to go over here, but just a little introduction to P and NP class problems. So you have these problems that are kind of like P problems, where a solution is easy to find. And now by easy, the definition of it is that a solution can be found in polynomial time. So the complexity of a solution increases in a polynomial way, but in relation to the size of the problem. So for instance, if I'm looking at just a graph, a chart of these things, and I want to say, find the smallest number in here, it's pretty easy to find it. As the number of options grows, it doesn't really get that much harder. I double the number of options that I have to look at, it doubles the complexity of the solution. I triple the number of options, it triples the complexity of the solution. I just have to look at 3 times as many things to find the solution. So that means it's polynomial. The polynomial difficulty, complexity of the solution is related to the size of the problem in polynomial manner. But we also have this thing called NP problems, where a solution is difficult to find. And by difficult, we mean non-polynomial time. So for instance, you've probably seen Sudoku. A Sudoku solution is relatively difficult to find. And now if you think about Sudoku, it uses the numbers 1 through 9, but really it could be as large as possible. If you double the size of it, it's more than doubling the complexity of finding a solution. The complexity of finding a solution grows in kind of an exponential manner, more than polynomial time. So Uh, Anything that involves um, permutations or combinations to find the number of solutions often has a non-polynomial complexity to find the solution. When it as the problem grows, finding the solution grows exponentially. Okay? NP problems also have a property that it is easy to verify. So if I give you a solution, I can find it very easily. No, I give you a solution to a Sudoku, it's pretty easy to see that it is a solution, but finding that solution is much more complex. So we have this concept of P problems and NP problems. When you get into the realm of NP problems, it means that as the problem grows, the difficulty of finding a solution grows exponentially. That's when you start dealing with heuristic solutions and where heuristic solutions become very important. Just another little footnote to the P and NP class of problems. Um, it's never been shown that they are different things, that there isn't a way to solve certain non-polynomial problems with polynomial solutions. It's possible that we just haven't found the solution method yet. If you can solve that problem, if you can show that they are the same thing or prove that they are different things, there's $1 million reward for it. So just a little sideline on the complexity of problems. But we're going to look at a couple of methods for heuristic solutions of problems, just to give you a little taste of them. So for instance, a greedy search or a greedy heuristic solution. So we have, in general, when we're dealing with optimizing things, we can say we're minimizing a function subject to x in S. So minimize the value of your function where your feasible region, or for any point in your feasible region. That's essentially what it comes down to. A greedy search just says start with what you think might be the best thing and keep taking the best thing at that point. So in a little bit of a mathematical algorithm, you start from a random point, and at any step in the algorithm where you have a point that you're at, find the next point by choosing the best one in the neighborhood, and then keep going until there's no improvement possible. Now, if you look at this, what do I mean by neighborhood? Well, that depends on the problem. Neighborhood could mean take the next option available. It could mean look within 1 unit of the point you're at now. It depends on the problem. But the idea is that you aren't searching everything. You're searching the things that are close to it and finding the best thing that's close to where you are now until you can't make any more improvements. So one example of this is a classic example is a knapsack problem. And this is an NP problem. It gets very complex the more options you throw into it. So there are lots of ways of formalizing it. One way is saying that a thief breaks into a store, wants to steal as much value as he can, but he can only carry so much. So that thief can only carry 50 kilograms, but every item in that store has a different value. How does this thief choose what to steal? The greedy solution to the problem says, start with the item that will fit in your backpack that has the highest value. That takes up a certain amount, say it takes up 30 kilograms, you're left with 20 kilograms. Find the next item that is 20 kilograms or less with the highest value. If that takes up 15 kilograms, you're left with 5 kilograms. Take the next item that's no more than 5 kilograms that has the highest value and just keep going until you've reached your limit. That's essentially the greedy algorithm. We have already seen the greedy algorithm. Remember when we were doing the transportation algorithm? We started with an initial feasible solution. How did you get that? You started by saying put as much product through the smallest cost link and go from there. And then take the next smallest and the next smallest cost. We use the greedy algorithm to find our initial feasible solution. So that's the greedy algorithm. That's a pretty simple one. And that's a pretty easy one to see. Meta heuristics are for getting you out of a local optimum. So when you're using the greedy algorithm, the problem is that you can get an optimal value, but it may not be the exact optimal value. So for instance, if you have something like this, you could use a greedy algorithm that, you start here, you kind of jump over to here, and eventually you end up at this point. But remember, the greedy algorithm says look in the neighborhood and find the next best solution. Well, if you define your neighborhood here to be anything within where your x is within 1, what are you going to get? You're going to be looking in here, and you're going to say, I'm at the best solution. I'm never going to do any better. Well, the problem is if you would look just a little bit farther, all of a sudden, you'd see that there's a better solution. If you look a little farther yet, you'd see there's an even better solution. So greedy algorithms can get trapped in a local optimum. Meta-heuristics are algorithms that are designed to try get you out of a local optimum. And they take some customization depending on the problem you're doing. They are not guaranteed to get you the optimum for your problem, but they're to help you get a very good solution. So we're going to look at two of them. One is called a taboo search. So a taboo search just says, I am going to keep looking. Once I find my optimal solution, I'm going to keep looking with the rule that I'm not allowed to go back to where I've been before. And my rule for going from one point to another is going to be not do I have a better solution, but what's the best solution in my neighborhood, in my options. So what's here is the algorithm for it. So you define a taboo tenure period. In other words, saying that I'm not going to look anywhere else other than, or I'm not going to repeat myself if I've already found it in the last 5 moves or something like that. You start from your initial point, your initial feasible point. Then you look in the neighborhood. Find something in the neighborhood. Find the best thing in the neighborhood. Take that. Even if it is not, even if it's a little bit worse than where you are, you still take that point. Then from your second point, you look around the neighborhood and say, okay, what's the best thing that I can do now? But I'm not allowed to go back to where I just came from. So I have to find a new point. This will tend to take you in steps out of an optimum, out of a local optimum, and kind of try to get you over the hump where you can start looking at another minima for your function. Now, when you're playing with the taboo search, there's a lot of variables that you have to set. You have to understand what your neighborhood is, how you select things in the neighborhood, how long your taboo list is, and so forth. But just as an example, and this is a very, very basic example, you'd actually get a better example if you started to look at this as a three-dimensional function. But we just have a chart of numbers. So our taboo search would say, okay, start with the first one. Look in the neighborhood being its neighbors. Well, what's in there? Well, you have P2. So P2 is better, so that becomes my new one. Now what's in the neighborhood? Well, P3 and P1 are in the neighborhood. P1 I'm not allowed to go back to. I was already there. P3, well, it's not as good, but I'm going to say it's the best one in the neighborhood that I'm allowed to go to. So that's where I'm going to go next, but I'm going to remember that P2 was a better solution. Now P3, I look again. What's in the neighborhood? P4 and P2. I'm not allowed to go back to P2. I can go to P4. Oh, that's an even better solution. So forget about that. And my new best solution is at P4. Start looking in the neighborhood again. P5. It's no better, but that's my new point. Now I look in the neighborhood again, P6, and you just keep going like this. You just keep looking in the neighborhood to find the best thing in the neighborhood you can move to, forgetting about where you've been before. That's a taboo search. And you can see in this very simple example, if you had a greedy algorithm and you jumped from P1 to P2, you would have stopped there because its neighbors were no better. The taboo search says, we're forgetting about that one. We're going to just kind of jump around a little bit in the neighborhood and try to get out of that. And the taboo search leads you to the next minima. So that's the idea of a taboo search. Another concept is simulated annealing. This one's a little bit more complex, so it's hard to come up with a simple example to describe it. But here's the general idea for it. Simulated annealing introduces a probability for it. So every iteration, you define something called a temperature. So a temperature being a probability. And I'm going to say that, so the probability might be 70%. At each, for a single step. At each step, you are going, if you come up with a better solution, you take the better solution. If you don't have a better solution, then you randomly say, okay, there's a 70% chance I'm going to go this way anyways, just to start moving away and to try get to another place where there might be another minima. So you start with your starting solution in a neighborhood. Again, you have to define what your neighborhood is. At every point, you find your next step, you pick something random in your neighborhood. If it's a better solution, or if it's no worse, you say, I'm going to accept that solution. If it's not, in other words, if you're jumping to a point that's worse, I might accept it anyways. I'm going to roll the dice and see what my probability is. If it's better than my probability, I'm going to go there anyways. So you just kind of jump around randomly in random directions. This temperature, if you keep it high, it means you're going to jump around an awful lot. If you make it low, it means you're only going to jump around locally. So when you're doing simulated annealing, you tend to start out with a high temperature, which lets you jump to a bunch of different places. And then you go to a lower temperature, which kind of keeps you constrained in a certain area. So you're kind of exploring your feasible region at the start by going to a lot of places randomly, finding where your best options might be, and then from there you narrow it down and just keep looking in the general vicinity of what your best options were until you find something that's kind of the best thing. And when you determine when you stop, well, you could say that I'm going to do this 100,000 times and see what I get. So you could have rules like that. There's all kinds of different rules as well, depending on what you're doing. But simulated annealing is starting to introduce the idea of a kind of a random walk around your feasible region to try find your optimum value. Okay, so those were just a little bit of heuristical solutions. Now remember, we've spent almost all this course looking at linear programs where we have very, very good solutions to solve them. We looked at simplex method, variations of it like the transportation, Hungarian method, dual simplex, and so forth. Those are all very structured, very easy ways to solve these problems. The reality is that most problems aren't going to be that nice. You are going to have to work with a lot of messiness. Heuristics and meta-heuristics give you another solution, another approach to find an optimum when sometimes finding the perfect solution is not worth it, and you're happy to get just a very good solution instead of the optimal solution.